Okay guys, today we're doing section 3.6, variation of parameters. This is a second general and long method of solving non-homogeneous linear equations. I'm going to start with a basic idea. So let me write down this is a second general and long method. I'm going to start with explaining idea again on equation of the first order. So idea. Consider equation of the first order. Y prime minus y equals 3e to the power of t. Homogeneous solution r minus 1 equals 0 means that r equals 1, or y homogeneous equals c e to the power of t. Remember that in previous section I was telling you in this case we'll need to multiply by t for particular solution. So we cannot use actually this solution for particular solution just because homogeneous solution will turn this side into 0 and we are going to have nothing to make equal 3e to the power of t. Right? And in previous section I just multiplied by t and told you that I'm going to explain it later. That's the time when I'm going to explain it. Remember we had a reduction of order, right? And there is a general method of finding a second solution if you do know one solution. Remember, it was representing a second solution as a constant of the same variable, in our case t, multiplied by first solution. It's called variation of parameters. So basically, we are going to vary the constant and find out what is supposed to be a function if your solution must look like this. Does it kind of make our solution necessarily, or particular solution necessarily be equal e to the power of t? No. Actually, constant c of t can be equal e to the power of negative t by sine of t. And then e is going to disappear and y is going to be pure sine. So basically this is just formality. Imagine that you take solution y2 divided by solution y1 and then multiply by solution y1. Then this ratio can be called a constant, but actually it still has this unknown function, right? Let me show you how it's going to help us to solve equation. First, I'm going to differentiate it. Because it's a product now, I'm going to differentiate first c multiplied by e to the power of t, and then differentiate e to the power of t, which is going to give me still e to the power of t. Well, if you look at my derivative, and imagine that c is not changing with t, c is just a constant, then derivative is going to be looking like this. So this is old derivative. If you were differentiating just this function, it would be just c e to the power of t. And I'm going to call this extra. Let's plug into equation. What are we going to have? C prime e to the power of t plus c e to the power of t minus, my solution is c e to the power of t equals 3e to the power of t. You see that old derivative, which was sitting over here, and my actual solution, which is looking like old solution, if you kind of pretend that c is a real constant, not changing with t, are going to cancel each other. Why? Because this is e to the power of t is a general solution, homogeneous solution. So homogeneous solution always solves homogeneous equations. So they will turn into 0. And what we are going to have, it's c prime e to the power of t equals 3e to the power of t. Well, we can divide by e to the power of t because it's not equal to 0, right? And we are going to have c prime equals 3, from where very easy to find what is c. Just anti-differentiate both sides, right? It's 3t plus a constant, which is a real constant, right? I'm going to put here c of t to separate this c from this c. Now my solution is going to look, if I plug back my c of t as 3t plus c e to the power of t. And if I multiply it by e to the power of t, I'm going to have 3t e to the power of t plus c e to the power of t. And we recognize here our homogeneous solution. And this one can work as our particular solution. And you see that in our particular solution, we actually do multiply it by t, and that's going to just give us extra coefficient. Well, we're going to apply same method of variation of parameters to a second order equation. Unfortunately, in second order equation is going to be a little bit more complicated, but idea is going to be basically same. Let me kind of point on idea. So when you do variation of parameter and apply a product rule to product of changeable parameter and e to the power of t, or any solution, you are going to get one derivative looking like old derivative, just multiplied by a constant variable function. And the second derivative is going to be different, extra. So it's like old derivative and extra. Old derivative and old function, they fit into homogeneous equation. They're going to disappear. The only thing we are going to have extra. If we make this extra to our right side, we can find actually what is c, right? Because this part disappears and we can just calculate c. We can basically solve, even if e to the power of t and e to the power of t do not disappear here. For example, you have here sine. We still can kind of find the antiderivative, right? It's just a derivative of some function equals to a known function. We can integrate it. We're going to apply same method to second order equation. It's going to be a little bit longer, but not impossible. I'm thinking to give you some theory, and for theory I want to use general equation. So second order theory for linear non-homogeneous equation. So what is my linear non-homogeneous equation? Second derivative plus p of t, first derivative plus q of t function equals g of t. This is my second derivative non-homogeneous equation. General, not with constant coefficient, but with some changeable coefficients. This method is going to be applied to this equation too, not like to only the simplified version which has constant coefficients. Okay? So let's imagine that we do know homogeneous solution. So imagine that we know homogeneous solution y homogeneous, which equals c1 y1 plus c2 y2. Sorry, solution. So here y1 and y2 are functions which are like solutions of this, right? Two solutions, right? c1 and c2 are just normal constants. Now, applying variation of parameters, we are going to search for solution of non-homogeneous equation as c1 of t, y1 of t. Here y1 was of t2, just c was not of t. We do variate parameters. Parameters are just constants in front of our solutions. To do this variation, we are going to need the derivative and the second derivative, right, to plug back into the equation. So first derivative, well, product rule, c1 prime y1 plus c1 y1 prime plus c2 prime y2 plus c2 y2 prime. I'm going to rearrange it a little bit. I'm going to arrange terms with c1 prime and c2 prime separately from terms c1 y1 plus c2 y2. Here, guys, c depends on t. But if you imagine for a second that c does not depend on t, then derivative is going to look like this. So this is kind of old derivative multiplied by function. So c is changing with time, but otherwise it's very similar to old derivative. What is this? This is extra. Let's set our extra to 0. just to to not have too many terms. And find the second derivative. We just want to get a first derivative same as it was before when we did not change C1 and C2. Second derivative. Well, because this is equal to 0, I just differentiate this part. And because of product rule, I'm going to get a kind of same C prime, Y1 prime plus C1, 1 second derivative plus C2 prime, Y2 prime plus C2, Y second derivative. Again, I'm going to do same operation. I'm going to combine together terms with derivative of the constants or parameters and terms which are looking like old derivative. So this looks like old derivative. If you don't write down here t next to c, it's going to look exactly like old derivative, just like derivative is derivative of the function only, right? This looks like extra. It would be nice to set up extra not to 0, but to function g of t. Why? Let me explain you why. So I'm going to substitute everything into this equation, and I'm going to remember that homogeneous solution solves actually homogeneous equation when g equals to 0. So let me kind of do substitution of the second derivative, the first derivative, and the function itself, okay? So I'm going to start with extra term. C1 prime, Y1 prime, plus C2 prime, Y2 prime, plus C1, Y1 second derivative, C2, Y2 second derivative. From this one, we already set it to 0, so we're not going to copy it. We're just going to copy this. And for this one, we're just going to copy it. I'm not going to write down t. I'm going to write down C1, Y1, plus C2, Y2. And it's supposed to be equal to g of t, right? Sorry, and I'm missing something like p and q. Let me put, so there is supposed to be actually p in front of this one. Let me put plus here and p over here, and q in front of this one. Well, I cannot fit anything in front. I'm going to put q behind. It's not going to change anything. What I'm going to do, guys, because I set my extra to g of t, I'm going to, because I said already, well, let's find the C1 and C2 such functions that it's equals to g of t. It's going to cancel this and this. What is going to happen here? I'm going to combine terms with y1 separately from terms with y2. I have C1, y1 second derivative plus p, I'm combining this term, y1 first derivative plus q, this term, y1 plus C2, y2 second derivative plus p, y2 first derivative plus q, y2, and these are only the terms left, supposed to be equal to 0. Is it equal to 0? Well, here c depends on t, so c is not actually a constant, but because y1 is a homogeneous, is solution of homogeneous equation, when we plug it into homogeneous equation, which is equal to 0, it's going to solve it. And this one is going to solve it too. I'm going to write down because y1 and y2 solve homogeneous equation equals to 0. So they are going to be 0. So everything is becoming a true statement. So if we did not set up this little extra to g of t, we are going to have them left over. G of t and this one are going to be leftovers. But if we do set them up equal to each other, we are going to have two equations on the constants. If you look at this condition, that's actually equation, and this condition is also actual equation. Let me write them down separately. So my first equation is C1 prime y1 plus C2 prime y2 equals 0. C1 y prime plus C2 y2 prime equals g of t. You will look at this and say, okay, instead of like having one equation of second order, we have two equations about two different unknown functions. Yes, but what is good about these two equations? If you look at this system and forget for a second that C1, C2, and they're derivatives of something, and you label them x and y, you do know y1 and y2. You find them when you solve homogeneous equations. So you do know g of t. So basically, for this system of two unknowns, c1 prime and c2 prime, you can solve it just like normal linear system, like ax plus by equals d, and fx plus y, zy equals, I don't know, c. So this is a system of two equations with two unknowns. C1 prime and C2 prime. And we can actually solve it. It's not very difficult to solve it in general. Well, let's do it once. Again, normally, guys, we're not going to use any formulas when we do solution, but we just can solve it once to show how the formula is going to look. So what I'm going to do, I'm going to, for example, express C2 from this first equation. So C2 prime equals C1 prime divided, multiplied by y1 divided by y2. We do know y1 and y2. Then plug it in here, plug it into the second equation. So we have C1 prime, y1 prime plus, oh, sorry guys, I forgot a minus here. When I was moving this to the other side, it's minus. So minus C1 prime y1 over y2 prime equals 2g of t. Well, C1 prime repeated 2 times, so I'm going to take it outside of parentheses, and in parentheses I have y1 prime minus y1 y2 prime over y2 equals g of t, from where C1 prime equals g of t. Well, maybe I should kind of multiply by y2 here. So y2 by y1 prime minus y1 y2 prime. And I'll need to divide by y2, right? Divide by y2. But when I have it in denominator, I multiply by y2. Well, we got a general formula for c prime, our unknown function, right? And we have everything known on the right side. G is known because it's going to be given with equation. Y2 and y1 are known because we do know homogeneous solution. And derivatives of these homogeneous solutions are also known. You just plug everything into this formula and get cy. C1, yes, it's going to be a derivative. And we'll need to take the integral to get actual C1. So actual C1 is going to be integral of this g of t, y2, but it's not impossible to calculate, right? And nice general formula we have. Same way we can calculate C1, C2. I'm not gonna, well, we just take this formula and plug it in here, and that's going to give us C2. The only difference for C2 is going to be, because they're symmetrical. Did I miss a minus anywhere? It's going to be just y1 here and maybe change of the signs here. I usually prefer to not use the formulas, just because formulas disappear very quickly from our heads. My suggestion, remember the idea. Well, now maybe we should solve something, because the best way to learn is to solve an example. So I'm going to consider example. Example. I'm going to consider very simple equation, but my right side is not sine, not cosine, not exponential, not polynomial, not mix of them. It's tangent. It's mix of sine and cosine, but not as a product, as a fraction. So here, if I was trying to solve it by undetermined coefficients, I won't be able to do it. So this problem is specifically solved by variation of parameters. Let's see how do we solve it. So I'm going to start with homogeneous equation. It is going to give me r squared plus 1 equals to 0, from where r equals plus minus I, from where my homogeneous solution is c1 cosine of t plus c2 sine of t. Well, it's just like, because lambda here equals 0 and mu here equals 1, right? That's a homogeneous solution. Well, I don't want to actually repeat all my kind of theoretical calculations I was doing. Like, I'm just going to use equations. If you look at these equations, they're very symmetrical, right? First, they do have C1 prime and C2 prime, right? And they repeat it in both of them. For the first line, which is equal to 0, we just have functions. For the second line, which is equal to your function, we do have derivatives. Well, I'm just going to use this system. I don't want to use the final answer. If I do the final answer, it's not gonna like feel like I'm solving anything. It's going to feel like I'm just plugging everything into the formula. So I'm going to build a system. C1 prime y1 is cosine of t plus c2 prime sine of t equals 0. C1 prime. Now here I need a derivative of the first function. Derivative is minus sine of t, right? Here derivative of sine is cosine of t, and my right side is tangent of t. Okay, good. Well, actually, solution is going to just follow the steps of general solution over here. So I'm going to take C2 and write down C2 prime equals minus C1 prime cosine of t over sine of t. And then plug it into the first equation. Plug it into the first equation is going to give me C1 minus sine of t minus, sorry, missing a derivative, C1 cosine of t sine of t by cosine of t and equals tangent of t. Tangent did not squeeze here. Okay, what I'm going to do, I think I'm going to square this cosine and take C1 outside of parentheses. So C1 prime is minus sine of t minus cosine square of t over sine of t and equals tangent of t. Bringing to common denominator here, I'm going to get C1 prime, and I have, maybe I should take minus outside too, minus here, sine square of t plus cosine square of t, you already guessed what is it, right? Sine of t equals tangent of t. And because this is equal to 1 due Pythagorean identity, what I'm going to have, C1 prime equals minus tangent of t multiplied by sine of t. What I'm going to do, guys, I'm going to find C2 prime and then integrate both of them, okay? If you don't mind. I want to leave integration to the end of the process. So according to my formula, C2 prime equals minus C1 prime, which I'm going to copy. It already has minus, so I'm going to put plus here. Tangent of t by sine of t. And then cosine of t by sine of t. Wow. I think I can cancel something like sine and sine here, right? And tangent is sine over cosine, so I'm going to write down sine of t over cosine of t. Cosine of t is going to be cancelled too, so I'm going to get the sine of t. Well, actually, I do like the C2 to solve for integral because I'm getting just sine, right? Very easy to integrate. So C2, it's integral of sine of t dt, which is going to give me cosine of t with minus plus a constant, which I'm also going to label C2 because this C2 is function of t, but this C2 is a real constant, right? Okay, so I found C2. Now I'll need to integrate this. I'm thinking how to kind of modify it. Okay, let's do it. Wow. Okay. C1 integral of tangent of t by sine of t dt. Okay, I'm going to bring it as to sine over cosine. So sine of t over cosine of t by sine of t dt. I'm going to do, I'm going to represent sine, which is sine squared here, as 1 minus cosine. I don't want to really integrate, I just want to use the ready formulas. Now I'm going to divide each term here by cosine, so I have minus 1 over cosine of t dt plus this minus and this minus integral of cosine of t dt. I'm a little bit lazy today. What is 1 over cosine? That's a secant, right? We do remember that integral of secant is ln of what? Secant plus tangent, right? Secant of t plus tangent of t. And the integral of cosine is going to be just sine of t plus a constant. Well, I'm going to label it constant c1 because this c1 is actually a function of t. Oh, okay, kind of we got it, right? Now what we'll need to do, just kind of plug both constants back into our non-homogeneous solution and give it as a final answer. Let me move it up. So remember that homogeneous solution was y homogeneous was c1 cosine of t plus c2 sine of t. Now I'm going to write down non-homogeneous solution or general solution. Instead of c1, I'm going to write down this crocodile. Minus ln secant of t plus tangent of t plus sine of t plus c1 cosine of t. Plus, instead of c2, well, c2 is kind of cosine of t, minus cosine of t plus c2 sine of t. I'm going to open my parentheses to simplify it a little bit. Minus ln secant of t plus tangent of t multiplied by cosine of t plus sine of t cosine of t plus c1 cosine of t minus cosine of t sine of t plus c2 sine of t. What I have this term, they're exactly identical, so I'm going to cancel them. What I have, what is this and this? That's homogeneous solution, right? So what is this? That's going to be my particular solution. I'm going to write it down and then separately write down particular solution and homogeneous solution. Cosine of t plus c1 cosine of t plus c2 sine of t. So I'm going to write down y homogeneous and I'm going to label this one as y particular. Well, you see, we don't need to do any guessing anymore, and you can solve all the problems you were solving in previous section, not by undetermined coefficients, but by this method. It's just going to be much longer. You see how long it takes one problem only. Undetermined coefficients are going to take like 2 seconds to solve. Okay, so what else do we need? I think we can consider one more example. Let's do it. And maybe that's going to be it. Unfortunately, I cannot make a lecture of like 2 hours long. No one is going to watch the video. So example 2. Second derivative of y minus 2y prime plus y equals e to the power of t over t. Again, you see that's a combination of exponential and polynomial, but they are not combined as a product, they are combined as a fraction. That's going to be a problem. So we start with homogeneous solution. R squared minus 2r plus 1 equals 0. Looks like a perfect square, right? R minus 1 squared equals 0. So we have a double solution. R equals 1. Repeated root. So my homogeneous solution here is going to be C1 e to the power of t plus C2t e to the power of t. Remember, repeated roots, we multiply by t, right? That's my homogeneous solution. Now I'm going to do variation of parameters here and just I'm going to again use my equations. So let me write down equations, otherwise it's going to be like too hard to plug everything in. They're very symmetrical, not difficult to remember actually. The first one and the second one. Again, this one is extra for the first derivative, and this one is extra for the second derivative we are making equal to g of t. Well, we just kind of, we can label this as y1, and this is y2. Sorry, forgot the derivative here. Let's differentiate y2, because y1 is easy to differentiate, but y2 it's a product, right? So I'm going to substitute c1 prime y1 is e to the power of t plus c2 prime, and y2 is t e to the power of t, supposed to be equal to 0. c1 prime, derivative of this is still e to the power of t, c2 prime, product rule. So I differentiate first t, it's e to the power of t, and then differentiate e to the power of t, and equals to g of t, my function on the right side. Major problem here, guys, is to not get the answer for derivatives, but integrate, actually get integrable function after you kind of have a derivative. So here we were lucky, we were able to calculate the integral, but it's not always going to work. But mathematicians don't care about this. If you write it down as integral, they're happy. Well, I think I'm just going to apply same tactics. Maybe I'm going to cancel all e of t, e to the power of t everywhere, just because it's never equal to 0. And for the first equation, I have c1 prime equals negative c2 prime t, right? I'm just moving it to the right side. And for the first equation, c1 prime plus c2 prime 1 plus t equals 1 over t. So I just canceled all exponential factors. Normally we don't do it, but here we do know that it's greater than 0, so we're not kind of breaking any laws here. Well, I'm going to plug in c1 into my second equation, do a little variation. So minus c2 prime t plus c2 prime plus c2 prime t equals 1 over t. Why I did this? Well, because I was expecting that these two terms are going to cancel, and c2 prime equals 1 over t, which is easy to integrate. Then c2 equals ln of t plus actual c2, right? This c2 is of t, but this one is real c2. Not bad. Let's do c1. Well, for c1, we're going to have c1 prime equals minus c2 prime was 1 over t multiplied by t, 1 over t here, multiplied by this t is going to be negative 1, means that c1 is going to be minus t plus c1 as a real number constant. Well, now we plug in everything back into our equation to get our non-homogeneous solution, which is general solution, same as general. So c1 is minus t plus c1 e to the power of t plus ln of t plus c2 t e to the power of t. I'm going to open parentheses because I want to show you where is going to be general solution, where is going to be a particular solution. So minus t to the power of t plus c1 e to the power of t plus ln of t multiplied by t e to the power of t plus c2 t e to the power of t. This is going to contribute to homogeneous solution, right? And whatever is left over is going to be non-homogeneous. So I'm going to kind of copy leftover separately. We do have same term as t and e to the power of t, right? And minus 1 from this term, and plus ln of t from this one. And c1 e to the power of t and c2 t e to the power of t. So homogeneous solution, and that's going to be a particular solution. Okay, so we kind of did two examples. I wish I can do more, but it's already like 34 minutes. So guys, try to do homework. There are not too many questions which are solvable after the point you find the derivative here and the derivative here. Well, here we were lucky, right? There are not too many questions which are solvable. Usually you get derivative here, which is integral of something which you cannot actually integrate. Analytically, you will need to integrate numerically. Otherwise, not difficult. And all the answers are going to be same with the previous section. Just previous section is going to give us faster way to solve it, and this one is longer. But this is more general, and it solves more functions, even as a formula or even as an integral. Okay. Well, I think that's it for today's lecture. And if you have any questions, put them in question and answer discussion.